Welcome to the Analytics Engineering Podcast, featuring conversations with practitioners inventing the future of analytics engineering.
On this episode, Tristan and I sit down with Jonathan Frankle, who's the chief scientist at MosaicML, which was recently bought by Databricks for $1.3 billion. Mosaic is an exciting company that helps customers train generative AI models on their data. Lots of companies are excited about Gen AI, and the hope is their company data and information will be what sets them apart from the competition. This is a fun episode because we venture a bit outside of analytics engineering to learn more about a potential future where you can train specialized, purpose-built models. We learn about the process of training and serving models, why you might want to own the model yourself instead of using a general purpose one from, say, OpenAI, and the future of MosaicML inside of Databricks.
Did you notice when I tried to get him to comment on Databricks and yeah,
she's trained now,
the bigger strategy? Oh, it's too clever. No, this was a fun episode with Jonathan. I feel like we have in the past covered some of this ground before, but we got a new perspective from Jonathan. It really seems like Mosaic has done a lot of work to make training your own models more achievable than we have heard in the past. In the past, the advice that we've heard from guests on the show has been very focused on don't train your own, do retrieval augmented generation, do pre-train, like these other approaches, but there was generally you should shy away from doing your own model training. But Jonathan outlined a very clear kind of ladder to climb up. Like, here are the different approaches. Here's how you should progress through your experimentation in terms of which approach is right for you, which I thought was really compelling.
Yeah, I like this episode a lot. I think he's just a very compelling speaker too, because he comes from a very different background where he's an academic, but he also has interests in the legal profession, policy. So he comes with a wealth of information about, how to do this right. And we get to touch on not just MosaicML, but just the broader ecosystem as well. And I thought it was a fun episode. So without further ado, let's get into it. Jonathan, welcome to the show. We're super excited to have you.
Thank you so much for having me. I'm really excited to be here.
In doing my investigation on your background, you have an extremely impressive background, but you've done a bunch of different things before joining MosaicML, which was well known for being recently acquired by Databricks for $1.3 billion. You're chief scientist there, but you were doing some academic work. You have kind of an interest in policy as well.
Julia, did you see that Jonathan, I think at some point, was an adjunct professor of law?
That is correct.
Right. It's just it's like how many different interests you have and how have you expressed them so well. Tell us a little bit more about your background and maybe some of the unusual bits of how that all led to your interest in working at MosaicML.
Yeah, so it's a very long story depending on how far you want to go back, but the gist of it is, I'm a trained computer scientist. All three of my degrees are in computer science, and I caught the interest in machine learning relatively recently, all things considered. I've tried being a programming language researcher. I've tried being a cryptographer. I've tried doing technology policy, which is something I still do on the side, but, isn't my main focus anymore. But I've really tried all of it and, kind of found my way into machine learning during the second year of my PhD, and, research went well and I stuck around. But I did, on the law professor front, that is a true story, that I did do a year between my master's and my PhD at Georgetown Law, where I had the role of staff technologist at one of the centers at the law school. So my job was to be the technical person on campus. The law school is in a very different part of town from the main campus. And so I think, the most experienced computer scientist at the law school. Did a bunch of work on police use of facial recognition, and then taught a class on programming for lawyers. And if you teach and you have to issue grades at Georgetown Law, the only way you can do that is if you've got a faculty title. So they made me an adjunct professor of law for the semester, and I came back and did it again, I think, a couple years later. And it, great business card, great title on the resume, hilarious experience. I'm not a lawyer. Don't ask me any legal questions. I don't know the answer. And I've been around enough lawyers to know that I shouldn't know the answer.
I imagine that most law schools do not offer such a class, but I feel like that is very, very relevant today.
Many law schools do now offer a class kind of based on the curriculum we developed. It's starting to happen. So,
that's cool.
And there are plenty of law students who will go and take an intro programming class at the bigger university. At Georgetown, that was tricky just geographically. But there are a bunch of universities now that offer, a version of the class that we created or some, riff on the idea or something like that. So it is pretty exciting on that front. It's happening more and more. People debate whether it's worthwhile, but I just think it's great to give people hands-on experience with technology. It changes your intuitions and how you reason about things.
And Julia, I know that it would rabbit hole us for way too long if we got into like AI policy conversations. But Jonathan, is this an area that you have thoughts on for us to maybe return to later in the conversation?
Oh, yeah, definitely.
Okay.
If we have time, we should definitely chat about it.
Amazing.
Yeah, there's like a lot of threads I want to pull on, but let's jump into the present and we'll pop in and out on a bunch of different ones as we go. But bring us to Mosaic. What is MosaicML? Tell us a little bit about how you help companies like train their generative models. I think, to give a little bit of context, like this audience has more of a data background and they have lots and lots of interesting company data. And everyone's really curious about how do I bring that data in a way that's useful for the ML world to build models that can do like precision tasks or do things really well in the context of their business. And I think Mosaic really helps there. So tell us a little bit about what is Mosaic and what would be like the quick takeaway for people with data on how they can start thinking about this in their workplace.
Yeah, so the way to think of Mosaic is kind of, if OpenAI's goal in the world is to build one big model that can solve every problem, our belief is that you're never going to build one big model that can solve every problem because every problem is different and weird. And with that in mind, everybody's going to need their own custom model built around their data, their specifications, their goals, their budget, all that good stuff. And that's what we do. We've built the tools, the infrastructure, everything necessary so that someone can come, train a large language model or train a large diffusion model, or we can do a wide variety of different, big, complex deep learning models these days, train it on their custom data and get that model back and have it be a pretty pain-free experience. You come in, we've done it before, we'll do it again in the future even bigger, and you're going to get something good out the other end. That's really our business. We're not interested in building one great model. We build models and open source them mainly as a demonstration that we can build those kinds of models. But the focus is really on building custom models for you and your data. And it does make a big difference. I think about GPT-4, it's an incredible model, but it doesn't know about your internal business processes. At least it shouldn't. Otherwise, you've done something horribly wrong with your data and it ended up on the web where OpenAI scraped it. So if you want to have your data in your model, there are a lot of different approaches, everything from kind of doing retrieval augmented work and shoving it into the context and hoping for the best. And you can keep your fingers crossed that will work, but there are a lot of reasons why that may not be sufficient. The model really doesn't know the data. You've gotten the data in the context and you hope the model can use it. We have incredibly long contexts in terms of computational feasibility, but we don't necessarily actually take advantage of them. I don't think we know how to holistically evaluate. Your model read The Great Gatsby, but did it actually take advantage of all the content that was there? A lot of our exercises for evaluating long context are things like, I hid a password in there and the model could find the password. That means it can focus on one part of the context. Can it focus on everything? So our technical capabilities may run ahead of what we can actually do productively with the model. The next step is maybe you fine-tune the model in your data, and that's a great approach. You can get your data into the model. But sometimes you just got to build it from scratch. That could be anything from you care about what went into the model, and OpenAI and Meta are never going to tell you what they trained on, probably because they'd be pretty afraid of getting sued if they did, and perhaps rightly so. And, sometimes you just need to know what went in, and sometimes you need to determine it. You're training a model in a language that is not well supported or where you have a lot of data to bring to bear. You're training it on a domain that is not well supported or where you have a lot of data to bring to bear. And in those cases, we love doing fine tuning, but this is really our bread and butter. We build big foundation models for people who have a specific need to do so.
And can you maybe go into the distinction there between what fine-tuning a model means versus like having to pre-train a model from scratch? What does the process look like from a customer's perspective, and what are the outcomes and how are they different?
A related question that I have into your answer here, there's probably this spectrum of like what a customer is trying to do. And on one end of the spectrum, it's just like, well, that's a great fine-tuning. And on the other end, you're like, you have to start from scratch. And like, where do you start making those trade-offs between those two decisions?
Yeah, these are great questions. So I'll start by saying I hate the word fine-tuning. I feel compelled to use it because it's a word that people know and have an intuition around. But, fine-tuning used to mean you take your very big expensive model and train it on a few hundred examples, something very, very small. And fine-tuning now means everything from that to you take a model like Llama 2 and you train it on another 100 billion or trillion tokens, and people will still refer to that as fine-tuning because it's a second stage to training. So I like the idea of just thinking about stages of training instead. You have your first stage, which tends to be more generic. You have a second stage that tends to be more specific, but that's not always true. There are lots and lots of different paradigms you can go into. So I think of fine-tuning as a spectrum in and of itself. You start with, I'm going to do it on a very small amount of data and see if it changes my model at all the way up to, I'm going to take an existing model that I think is pretty good and throw all of my data at it, perhaps billions or hundreds of billions of tokens. I'm going to spend a huge amount of money fine-tuning. Fine-tuning is not very fine a lot of the time. And hope that that generic model gave me a running start. It gave me a better starting place to train on my data. And so often one decision that I see people try to make is, do I just train from scratch? Or do I take your existing Mosaic model or, Llama 2 or what have you, and do I start with that? And as far as I'm concerned from a business perspective, you're going to spend the same amount of money either way. You're going to train on the same number of examples. It's going to cost you the same amount. The question is really, do you take that running start? Is that running start helpful? Are you okay with potentially using a model that you have no idea what it was trained on as your starting point? Is that, okay from a compliance perspective? Are you comfortable with it? Great if you are. If not, you can start from scratch and do just fine. So it's really, fine-tuning means a lot of things. And I hate the word, but I feel like I have to use it. To answer the second question, what I usually tell people is walk before you run and crawl before you walk. Like it's a ladder and you have to climb from the bottom to the top.
Which is the walk?
So, let's work our way from flipping over onto our stomach to crawling to walking to running. When someone comes to me and they say, there's a thing I really want to do, my first question is, can GPT-4 just do that? Or is there a compelling business reason why you can't use GPT-4? If not, can Llama 2 do it? Can you just do it as it stands? I'll happily take your $1 million if you insist on giving it to me, but I'd much rather if you can solve the problem cheaply, you should start there and know that you kind of worked your way up. Okay, then I might ask, well, let's try doing a little bit of fine-tuning, a few hundred examples on Llama 2. Does that do the trick? I don't know. But, if it does, you really don't need to pre-train your own model. And in some sense, pre-training is kind of your last resort. It's a resort you often need to go to right now because there are limitations in a lot of the other approaches, hence we have a business. But the first thing I usually ask people is do the simple, cheap things. If you can solve them there, I'd rather you save your money. It's not a good sale for me if I just took your money unnecessarily. I want to take your money because I've delivered something of value to you.
And in this crawl, walk, run trajectory, where does retrieval augmented generation fit in? Or you didn't mention it and that was intentional. You don't think anyone should do that ever?
Oh, no. I think plenty of people should try it. It gets a little complicated though, because you can do it on GPT-4 or you can do it when you fine tune a model. In some sense, retrieval augmented generation is a bit of a paradigm. I kind of see it as almost an orthogonal axis. Retrieval, if you have a bunch of data in document form where it makes sense for retrieval, you should kind of try that at every step. Try prompting GPT-4. Maybe it already knows everything it needs to know. At least set a baseline there. It probably doesn't know about your internal business documents, but try it as a baseline. Then, do some retrieval. And in fact, don't even set up a vector database or anything. Literally take the document that you personally think is most relevant and provide it to the model and see if the model can do that. You want to give the model every advantage and see if it can solve the problem. Make the strongest case you can that you do not need to pre-train. And failing all those cases, then we should chat about pre-training. Even when it comes to pre-training, I will always tell you, train a 1 billion parameter model, then a 3 billion, then a 7 billion, then a 13, then a 30. You climb your way up. You should not go straight for that 30 billion unless you are really, really sure that you need it and really, really sure that your data will even work when you pre-train a model. This is still a very fuzzy science right now. And who knows if for some reason there's something weird about your data or the task you're trying to solve where no model can do this for some mysterious reason.
So one helpful distinction that I've been hearing people talk about is retrieval augmented generation is good for retrieving facts. So if there is a source of truth or some information that comes from a document.
Says who? I mean, I mean that, less tongue in cheek to mean there are no real rules here and there are not even really rules of thumb. We do not know anything about how these models really work. And so good at retrieving facts is very fuzzy to me.
Yeah, it's definitely blending. I think where the knowledge sits, whether it should be in the model and trained in the model, or if you can just bring the context to the model, is blurring more. And it's pretty hard to get the models to behave as you need them to.
It's more than blurring, though, I think. I think it's that even in that statement, you've assumed that, knowledge is an object in some sense that we can put into a model or that we can put into a context. I think we have all these mental models in our heads about how these things should work or might work or can work. And if there's one thing I've learned about deep learning over the years, it is assume nothing about intuitions or about how things might work. Don't even have a mental model. Run the darned experiment and measure the outcome and see which way things go. When it comes to retrieval is good at facts, that comes down to measurement, and that comes down to what a fact is as far as you're concerned and what kind of output you're looking for, whether it can handle your kind of data properly. So, and that knowledge may already be in the model somewhere to the extent that the model has knowledge to begin with and isn't just generating likely sequences, which, is in some sense what it's trained to do. So I really don't like and resist very strongly these kinds of frameworks. I think the answer is you should have a process for what you test and in what order, because, you should generally go from cheapest to most expensive and, fastest to slowest and work your way up. But I don't think we should try to bring our intuitions to bear about how these things might work on the inside. I think we should really treat them as black boxes.
Today or ever?
I think the two are the same as far as any business is concerned today. And I don't make predictions about the future. But I can tell you that state of play today is very much, we don't know why retrieval works necessarily. We don't know what it means to store knowledge in a model. We don't know why fine-tuning a model that has generic knowledge could work well or could not work well in your situation. We don't know why, there are all sorts of crazy things that happen. There was that great example of Stable Diffusion where someone used it to generate audio. If I remember right, you were generating I don't even remember the name, but these these graphs that were used to generate audio, and it actually worked reasonably well. That's really weird. That is not something I would intuit would work at all. Intuitions defy us here. And I really think we should, as a scientist, I treat this as a black box, and you should go in and just, data in, measurement out. Anything else leads us astray. That's when people build things and then don't measure them and deploy them. And that's very dangerous because they assume it should work because retrieval's good at facts or what have you.
Yeah, I think the whole workflow of how do we evaluate LLM-powered applications is changing quite a bit. Like you talked about, you bring a scientist lens to evaluating, and it's very different than in software development where things are very deterministic. Like if things broke, you can find the line in your code because computers are very, very literal. They do exactly what you tell them to do. That's simply just not the case in this world. And so the whole mental model of how do you know what is happening and how do you trust becomes more of a scientific process of looking at data and getting a level of kind of quality and how do you measure quality. These are all kind of a new practice coming out.
Yeah, evaluation is the most important open question right now. And I emphasize open question. Nobody has any clue how to really measure how well these things are working. If you're in a very specific business situation where you have a very specific, business metric, yeah, measure that. But in general, measuring how good is a model is just a completely broken question that we don't know how to solve right now. And none of these benchmarks or leaderboards do a good job. We are hoping that we can have some truth and some kind of sanity and some kind of clarity about what's happening. We as humans want that. We as scientists want that. We don't have it.
I don't actually know that much about how deep MosaicML is in the commercialization journey, but my guess is that you have some pretty sizable customers, that you end up on the phone with these customers and help them talk through some of these questions. And I'm just imagining you saying we don't know how to evaluate any of the things that we're doing in this space. What do people say to you who are trying to solve business problems when you say that?
Well, I say that in general, and then I say to them, but what does success look like in your business case? You're clearly measuring that somehow right now. You're evaluating employees who are working on it, or you have some metrics for success. How are you measuring that, and how do we translate that? But I think to some extent, customers like working with us. When you work with us, you also end up working with my research team. And I think customers kind of like the honesty and the clarity of thought about what we can and can't know and how we work around that. I think there are a lot of folks who are promising too much clarity right now, and it will always disappoint you. I'd much rather give people the direct scientific honesty and help them work from a place of understanding of what we do and don't know. My big belief about the field, kind of my philosophy, is that everything we think we know about neural networks is probably wrong. And the first step on your journey to knowledge is accepting that you know nothing. And so when people come in with a lot of knowledge or a lot of frameworks or a lot of belief about exactly what to do or how things work, they're going to be wrong. And when customers come in with that belief, they're going to be wrong. And my job is to help them get to a point of greater knowledge and help them get to a point where they can make sophisticated decisions about really weird, complex, messy systems. And that means being really, really honest about what I know as a person, what my team knows, what we know as a field. And I think people appreciate that a lot. I think it's one of the reasons people like working with us.
I don't want you to go through and divulge a bunch of customer secrets, but one of the, I think, most interesting questions in the field today is actually not technical, it's commercial. It is just, for all the talk, how many LLM-based systems are actually in production today?
A lot.
Where are they being used? What kinds of use cases are the most prevalent in terms of like production systems?
A lot of chatbots, a lot of systems meant to generate potential content that a human will eventually review. And something like GitHub Copilot is that. They're generating potential content that a human will review. It happens, it's very short amounts of content. It's reviewed very quickly. But there's just the autocomplete application is an example of that. Jasper doing marketing copy is an example of that. I don't really trust these models to make big decisions on their own. I don't think anyone should right now. But there are a lot of applications where it's expensive for someone to write something and cheap for someone to check it. Those are the great applications for LLMs right now. You do want a human in the loop, at least for most things. At least anything that has stakes attached to it, you probably want a human in the loop. But there's a lot of stuff where you're generating content that might be expensive. That's marketing copy, that's ideation, that's, even that code snippet. And it's really cheap for a human to check. Like Copilot is a great example of a very tight loop, and a lot of applications are a much bigger, kind of slower loop because there's more content to generate, but same idea. A lot of summarization, a lot of content extraction, they're definitely in use. And I don't think the case has been proven that they deserve all the hype they're getting, but they're contributing to production.
Yeah, it makes me think of a one-way hash function. It takes a tremendous amount of compute power to brute force it, but if you have the key, you can actually determine, like with almost no compute, that whether or not it is correct.
I think you should think of P and NP. NP is the class of all problems that are easily checkable. P is the class of problems that are both, easy to generate a solution and easy to check. We basically want NP problems. That's kind of, or, not precisely NP problems, but metaphorically for a human checker. We want NP style problems. That's where LLMs really shine right now.
So I want to go into an area you alluded to, which is like the need for precise models. And so the idea of having like maybe a fleet of well-tuned precision models that can do certain tasks really well, and they're smaller. So in comparison to OpenAI's like GPT 3.5 or 4 or Anthropic's Claude, which are really versatile and have an ability to know a lot of things. Like when I'm talking to customer support, I don't need them to tell me about, chapter 4 of The Great Gatsby. Like that knowledge is not relevant for the particular context. Help us understand a little bit more on what the future might look like. Is it going to be that you have really tiny models that do small tasks really, really well, and they know nothing about things outside of their tasks? Or what is the happy medium? And I'm already hearing your response of we know nothing about anything, but tell us like what you think are some strategies that might work well.
Yeah, I think what I want to avoid conflating is the model size and the model specificity in terms of what it works on. It's entirely possible that you have a highly specialized model that it's actually pretty big because maybe, you need a big model or big models perform better in that situation, or you have a lot of data and big models require it, but they're still highly specialized. So I do want to distinguish between those two.
Can you share a little bit more, like what makes the model large? Is it like number of parameters? What does that mean?
It's
Is
just
it size?
raw number of parameters.
Okay.
A model is big because it takes more compute to create a run.
Okay.
And so, domain-specific models are often smaller. And you can often get away with something smaller because you're not asking as much of the model. Maybe. But even asking a model to write natural language is asking a lot of a model. And to have a good conversation is asking a lot of a model, even if it doesn't need to, even if it's, conversant on every topic versus conversant on one topic in practice. So I don't want to, again, this is one of those we know nothing situations. The advice I always give is start small and work your way up. And, as you see the scaling behavior and as you see that things are getting better with each additional, level of scale, cool, you invest more. If you stop getting ROI, you stop. But the other piece is that I think, I don't want to make any statements about the underlying nature of how these things work, but I think I can make a statement about the field. We're seeing a lot of fine-tuning products start to pop up. Everything from fine-tuning Llama to GPT 3.5 fine-tuning that just got announced. That seems to be the direction the field is moving. People want customization. Otherwise, nobody would be building these products. Or we'll see these products fail in another few months and OpenAI will cancel this or something. But, everybody seems to be moving toward a customization-centric world. And, I think that's telling.
Can you help demystify what the process looks like to fine-tune? So you have an audience of people that have lots of data, very familiar with data prep in the traditional sense for like analytics workloads. But I imagine the data prep here looks really different. If you could walk through like a workflow of how do you partner with people to get the right kinds of company data, and what does the training process look like in practice?
Yeah, the answer is really you need a lot of text and a lot of relevant text, and you need to eliminate the low quality stuff. I think the jury's still out on whether you want to have only high quality text or whether you just want to have lots and lots of text. What is the quantity quality trade off? Obviously, if you have one very high quality sentence, that's not going to make for a great training set. So there is some trade off intrinsically there. We're still kind of figuring that out. We definitely think that eliminating the lowest quality data is probably important. And then beyond that, I think there are a lot of questions. But you need text, and you need it to be kind of in natural language sentence form. Like it needs to be, prose. Beyond that, there's a lot of experimentation that goes into this. There's a lot of work in figuring out, okay, which data seems to be more important for improving the metrics? How do I mix different data sources together? Because everybody's got dozens of data sources they can pull from. What kind of data is helpful? What kind of data is not helpful? Again, it comes down to how you measure. But even in wrangling the data, so we don't do data wrangling ourselves at Mosaic. That's something we can't help with. But there's this amazing company called Databricks, and they're really good at that. So you can see why, joining forces was a really kind of an obvious win for everybody. We can now offer an end-to-end solution where you can come and say, I would like to train a large language model, and here's how I'm measuring success. And we can work with you from where's your data and how do we get it in and clean and tokenized and ready to go. There's a really nice, easy process for that now. We'll take that data and train the model. There's basically an API call, and then sitting and waiting for the model to train for a while, to deploying that model and evaluating it in production and rinsing and repeating over and over and over again until you're happy. And that's now an end-to-end process that we can offer within one company. I think that's pretty exciting. That's what got me excited about the potential acquisition.
Databricks is a close partner of ours, and we have a bunch of shared customers. I've personally used the platform. I'm probably not the biggest Databricks expert in the world, so it's possible that I'm going to be oversimplifying here. But my understanding is that really Databricks has a couple of core engines. It has the Spark engine, it has the Photon engine, it might have a couple of others. And that most of what Databricks has traditionally done, or is mostly known to do, is either process SQL responses or data frame responses. And, there's a lot you can do with a data frame. But my understanding is that the type of compute that you're using when you are doing the type of model training work that you folks do is that this is a different kind of compute. Like I don't think that a data frame paradigm plugs in nicely to that. Is this a new engine inside of Databricks? Like, how does it fit into the Databricks platform?
Yeah, so I would frame Databricks a little bit differently.
Okay.
I think of Databricks as a way of, it is a data transformation and manipulation platform that is able to summon the right amount of compute at the right times to make that happen, to keep costs under control very carefully, but able to get things done exceedingly fast within that restriction. Our data processing times at Mosaic went from like weeks to hours as soon as we moved everything over to Databricks post-acquisition. I see why they're a valuable company. I see why they provide business value. It's a great set of tools. That is very CPU-centric, although Databricks does offer GPU instances as well now. And there are a lot of workloads that involve a model at some step in a Databricks workflow and a Spark workflow where you do need a model in there and you need GPUs. Mosaic works mainly on GPUs, and we kind of have, we have our own, engine, our own software for that. But the handoff is very easy because, at the end of the day, we just take the data from Databricks and pipe it into our system, and we train the model. It's all pretty seamless. It's all at the end of the day working on cloud object stores. So it's just easy to connect data B. That's something we've already got done for our
another tool
internal
on top
models.
of the lakehouse.
Yeah, I wouldn't even think of it as another tool on top of the lakehouse. It's an extension of the lakehouse for doing different kinds of data processing in some sense. It's not formally a part of Spark, but I hope the product experience, and certainly for us internally, the product experience is already in a place where it kind of feels like just another natural step along the way. Cool, you prepared your data in Databricks, and then, the next step is that you plug it into Mosaic and you train, and then you plug that into, our inference serving pipeline, which I think is technically under the Databricks brand, but it's all connected and it's all one system at the end of the day. Just a matter of which brand you kind of want stamped on it and which things we focus on and which things, some of the other Databricks teams focus on.
And the nice thing about the cloud is that customers don't need to care about the edges too much. It all just kind of works. You integrate the documentation of both products. You probably make them available in the same APIs and command line, and you're just kind of off to the races.
At the end of the day, that's really it. You can almost think of it as, there are all these There are all these APIs you can call, one to process data in Spark, one to train a model with Mosaic. And at the end of the day, you're just orchestrating that pipeline. And from a product perspective, we can make that smoother and smoother and smoother now that we're working together on this. But at least, in the meantime, it's already incredibly smooth. I say that because we're doing it every day. And we've got it down to a science at this point, and that's the basis for now what we're passing on to our customers. And pretty much all of our Mosaic customers, at least, the ones I've spoken to lately, they're all really excited to use Databricks because we like it and they trust us. And we've told them that it's been really great for our data, and we really genuinely mean it. Like, it's saved us so much time because they built a great product over the past decade. And now a lot of our customers are looking into using Databricks as well for their data processing, even if they weren't doing so already. So, a lot of the pipeline's there and how people are using it, and things will get better and better and better as time goes on. We've only been at this, what's the date today? It's been like 6 weeks since the acquisition went through officially. So, we've made it pretty far already, and it's only going to get a lot better.
Okay, here's the last thing I'm going to ask on this topic, because I don't want to get you too far outside your...
No, I'm always happy to market, especially when there's a great thing to market. So please keep it coming.
Extend your experience here and the kind of very natural way that it seems like these platforms fit together. Does this seem like a natural way that the ecosystem will evolve, that data platforms, that most of the hyperscalers have a platform like this that they're building? Snowflake has their platform, Databricks has their platform. Like, do you think that the entire industry will kind of converge to incorporating workloads like this into the overall solution? Because it seems like a very compelling kind of package.
I don't like to speak about other people and what they're up to. And I don't like to speak about, the future. I think what I'll say is, I think we have an amazing product at Databricks, and I think it's great for customers. And, the ecosystem can do what the ecosystem wants to do, but we're doing our own thing, and I'm very happy with it. That's as much as you're going to get out of me.
The pipeline you described, it makes a lot of sense. You have the processing of the data in Databricks, then you move to the training in Mosaic, and you also serve the models and provide inference for your customers. So those models that have been trained, they're on data at a fixed point in time, right? They know everything that's happened since, call it August, is when the last time you sent maybe data. How often do you have to update your training? Is that a continuous thing or a continual process to update your models with newer information from your business? Or is it sufficient that you've done one really big training process, it knows everything up to August, and you're good?
It depends on what you're trying to do and whether time is a factor. There are a lot of situations where time just doesn't matter. You're a bank and you're processing, you've got a chatbot and you're giving customer service or something like that. Time may not be a factor. It may not matter who won the Super Bowl this year. And I think we kind of over-index a little bit on the idea of time and factual knowledge for something like GPT-4, which is trying to know everything about the world. But when you're doing code generation or marketing copy or what have you, time isn't really a factor. You update your model when you have new data or you think you can build a better model or the paradigm changes. But at the end of the day, time isn't that much of a factor. In other situations where time matters, I don't know if the New York Times wrote a New York Times article bot or something like that, kind of the epitome of time mattering. Or, you're Meta and you have recommendation models that need to change, updated with the, how the trends are changing on a daily basis, or, perhaps even more often than that. Yeah, time does matter. And, I think we've learned from the recommender system world, people do retrain really frequently where timeliness is important. And I would expect that to be the same thing here. Now, the question is whether you have to redo all of training or whether you can get by with kind of a shorter training run building on top of a model and appropriately mixing all the data together so the model doesn't over-index on recent data. That, I think, is still an open question right now. And I'd give the same answer I'd give anywhere. Try it and find out. I think there's a little bit of tinkering, and it's going to differ by data set and by application. And it's really easy to test because if you have your data set for, let's say the past 5 years, cool, just cut off 2023, train the model up to 2022, and then try a bunch of different approaches for incorporating 2023. Be it, training further on 2023, be it doing retrieval on 2023, be it training further on every year, including 2023, and maybe oversampling 2023. There are lots of hypotheses you could pose about the mechanism going on in the model. And, then you can test it and see kind of what seems to work.
So it's an all of the above process for your training, your retraining. Maybe you can add retrieval augmented generation on the trained model. And it's people just have to try a bunch of things out and see how the tests and evaluation of the end results impact the business.
Yeah, I think the answer here is, I don't know, data science is a very funky term that means a lot of things to a lot of people. And this to me is data science. You are legitimately being a scientist. You have to plan and run experiments to test out which approaches work and build accordingly. That's really everybody who's working with this stuff has to be a bit of a scientist. And I think, if I didn't love the term data science before, I now like the term a lot for describing what this process looks like. The trick is doing it systematically and doing it cheaply enough that you can eventually choose what you do at scale and pick one thing that you believe is going to work well and kind of put all your chips on the table and bet on that approach.
One other area I wanted to talk about is, you run on GPUs. So these are expensive, they're hard to come by, but there's rapidly changing in the ecosystem where the cost is coming down pretty dramatically and you have a lot of performance improvements as well. Where are the biggest wins coming from? Is it from the hardware? Is it from the algorithms that you're able to run on top of GPUs? Is it a combination? Just help us understand how the costs are able to move so quickly down in a space that's evolving pretty quickly.
I can't speak for the whole space, and I think in the whole space, costs aren't coming down that much, to be honest. The H100 offered better performance per dollar than the A100, just like the A100, offered better performance per dollar than the V100. And that has certainly reduced cost, kind of every 3 years plus. But on a kind of week by week or, month by month basis, it really is down to algorithm design and down to better ways of doing modeling. That's a bit of our specialty at Mosaic. It's kind of the topic that I did my PhD in.
Yeah, I was wondering if there was any correlation at all to the work you did with the lottery ticket problem.
Yeah, so I do look at Mosaic as an extension of my PhD. My PhD was all about studying one very specific aspect of how we can make training more efficient, whether we can delete a lot of the parameters and make much smaller models and still train them successfully. And, from there, Mosaic started when our CEO and CTO, Naveen Rao and Hanlin Tang, reached out to me and said, "Hey, nice paper, want to start a company?" And my answer was, that paper is useless for any practical purposes. And it is useless for any practical purposes. It's really fascinating science, which is exactly what I'm supposed to do in a PhD, but it is useless for practical purposes. But the idea that maybe we aren't optimizing these networks as effectively as we should or could, that we're not making all the best choices, that the reason we're training it this way is because it was handed down to us this way, not because it's actually the right way to do it. That's something that ended up being the basis of Mosaic. And our claim to fame still today is putting a lot of work into efficiency and really driving down costs to the point where anybody can afford this. And it's a lot of work. It's expensive to do, but it's really valuable. I think if we're going to offer custom models, we have to make it cheap enough that anybody can actually afford to do it. And that's still a big focus for us. We talk more about the overall benefits, but it is about cost at the end of the day, or at least cost is a necessary condition. It has to be cheap enough that anybody can do it. And we still focus on that very, very closely.
You were talking about crawl, walk, run. If you do need to train your own model, start with 1 billion, then 3 billion, and then, work your way up. In this efficiency view of the world, it certainly is more efficient to train and run inference on a 1 billion parameter model. But is the only path to get there to go from small to large, or can you start with a very large model? And is there a way to downsample it and to prune away that which is not necessary and keep the important parts? Or can you only step upwards?
You can do both. No, I recommend people step upwards because it is cheaper to train those models first. And if you're going to screw up, and you will screw up the first couple times, it's much better to do so when it costs $1,000 than when it costs $1 million. So I generally recommend to people that they start small and work their way up for that reason. Once you have a big model that works effectively, there are many ways of making deployment more efficient. You can prune it, although that's kind of less effective and less popular. You can quantize it, which is somewhat effective and very popular. And you can distill it, where you teach a smaller model to behave like a larger model, which is very tricky and very finicky. And I know very few situations where people have gotten it right. I'm guessing the turbo versions of the various models on OpenAI are distilled models. And often people have complained that, GPT-4 got a lot faster, but got lobotomized. I've heard that complaint a few times for various people in various applications. That sounds like distillation to me, where, it's not usually perfect, but it can make things much more efficient sometimes. The way I do think about it, though, is, if you're going to train a big model and then make it smaller, you should think about whether you could have just trained that small model for longer and, what the actual trade-off would have been. Would it have been that much worse than just training the big model and then training the small model? Distillation is expensive. It's not cheap. You still have to train a small model and do inference on a big model. And it's worth doing the math on, what is the cost and what performance can I expect?
What does it mean to train it for longer? Is it just more time or more examples?
Yeah, more tokens. more tokens and more time. So the llama models are actually a great example of this. There's this idea called, there's the paper about chinchilla. And the idea behind that paper was very simple. Suppose you've got a fixed amount of money, basically, that you're going to spend on training a model. What is the right trade-off between having a really big model versus having a small model, and training on a little data versus a lot of data? You could spend that whole budget by training a gigantic model for one step, or training a really tiny model for, trillions of steps. What is the right trade-off? And it did kind of outline what we consider to be approximately the optimal trade-off, at least for that particular setting, which was that you should train on about as much data, data equivalent to 20 times your number of parameters, approximately. That was kind of what we took away from Chinchilla. That's, if you're going to spend your compute, kind of do the math on how you fit together, model plus data on that model, which is 20 times the size of the model. And then, you're set.
So 1 billion parameters translates to you want to train it on 20 billion tokens.
Exactly.
So, okay.
As simple as that. But in the Llama model, Llama was trained on 7 billion parameters, or let's take the smallest Llama, 7 billion parameters. How many tokens should it have been trained on? I'm going to give you a math quiz. How many tokens is that then? 7 billion parameters, how many tokens?
It's like 140.
140 billion tokens. How many tokens was Llama 2 7 billion trained on? About 2 trillion. So one of the interesting parts of Llama is that the thing that was actually distinctive about it was that they trained for way longer than Chinchilla, than these optimal settings would say you should. So what they were doing was intrinsically suboptimal from a are you spending your budget wisely perspective. If they were going to train a 7 billion parameter model on 2 trillion tokens, they probably should have trained a bit much bigger model on fewer tokens. That would have been a more optimal choice that would have spent their budget better. The problem is that bigger models have some problems. They're expensive to serve, and they're finicky to train. The bigger the model, kind of weird stuff happens at large scales. And so actually, being suboptimal for training in terms of just spending your money wisely may actually be globally optimal when you take into account serving that model and how difficult it is to train and serve. And so, now we start to ask the question, suppose you came to me with a big budget and you said, I can train a Chinchilla optimal 100 billion parameter model. I might say to you, actually, I don't think that's the world's best idea. How do you plan to serve this model, and what do you plan to do with it? And how fast do you need it to run? Maybe the idea is that actually, let's be suboptimal. Let's only train a 30 billion parameter model instead, but train it for a bunch longer and spend our budget differently. You're going to spend more than you would have needed to get that quality from training, but it's going to make your life a lot easier when you have to serve that model. And it may even make training a little bit easier from the perspective that, things are less likely to fail. That was the real innovation in the Llama paper. They just pushed the envelope really far past what we thought was optimal. And it turns out the penalties aren't that high, all things considered. You're giving up maybe 15% in terms of you're paying 15% more than you should, or 20 or 30% more than you should, but you get a small model out the other end. That's kind of the cool part.
Got it. So you eat the cost when you train really large models, both on the training side, but also when you have to serve it, both from a latency and a cost perspective. So you have to think about the full experience, not just of the training, but what's it going to cost to serve inference.
Exactly. And how easy training is going to be. You want to train a 500 billion parameter model, that thing is going to be a nightmare to train. There's a lot of complexity involved in actually just getting it to run efficiently. And then optimization behaves in really weird, inexplicable ways that may lead the run to catastrophically fail. Smaller models tend to be a lot easier to work with.
And after you've trained your model, the artifact you get is the weights. Is that the thing that the company cares most about? Because they can take that, they own it, and can use that to serve their own model?
Yeah, you own it and you do whatever you want with it. We have our inference service that you're welcome to use, but you're welcome to just take it home and use something else. Replit open source the model they trained with us. That's fine too. We're really kind of training for contract in some sense. And what you choose to do with the model after that is your business.
This has been a tremendously interesting conversation for both of us. We asked this to all our guests to wrap up, but what do you hope will be true for the data industry looking 10 years out?
I hate making predictions about the future, so
I'm
not going to make any predictions about the future.
But it's not a prediction; it's just a hope. It's just
a hope, a wish.
My hope is that we'll all be a little more careful and thoughtful about how we relate to this technology. We will all respect it for its potency, but respect it for its sheer complexity and the impossibility of really understanding what's happening. And I think that's intrinsic. I really do think that the complexity in these systems is such that it is intrinsically difficult or impossible to understand what's happening inside. And so with that in mind, my hope is that we'll all be a little wiser and a little more thoughtful about what's happening and, how to navigate this, both, in day-to-day, what the tricks are for getting it to work properly and what the best practices are, but in general about how to be good scientists and how to be thoughtful and careful about what we're working with and how to understand the limitations of what we're dealing with. That's really my hope. I hope Mosaic and Databricks have a part in, making that a reality.
I love that. It's such a, what's the guy's name that hosted Cosmos last time?
Is that like Carl Sagan, or is that, Neil deGrasse
Sagan
Tyson?
did
Yeah,
it first. Neil deGrasse Tyson.
Yeah.
I feel like that's what Neil deGrasse Tyson would say if he were an AI researcher. He would be exhorting us to all take science seriously and invest the time and energy into thinking it through and doing it the right way. You've got a PBS special in your future somewhere.
Uh-oh. Don't tell Databricks that. I like my day job. I think we have incredibly powerful tools already. If technological development stopped today, we'd spend decades still getting more out of what we currently have and what we currently know. And I think that all comes down to we're going to have to be scientists in a way that as computer scientists, we've never really had to be before. And that's a new muscle that we're all going to have to learn to build. But I'm excited for it. There's so much more to get out of this technology if we do those things.
Jonathan, thank you so much for joining us on the podcast. It's been a lot of fun.
Thank you so much for having me. This was awesome. And, really excited to share it with all my friends at Databricks and otherwise once it's out.
Thanks for joining.
Definitely. Thank you.
The Analytics Engineering Podcast is sponsored by DBT Labs and is hosted by Tristan Handy and myself, Julia Schottenstein. Have comments, questions, or guest suggestions? Email us at podcast@dbtlabs.com. Our producers are Jeff Fox and Dan Poppy. If you enjoy the show, please drop a review or share it with a friend. Thanks for listening.